Welcome to section 10.3, where we are talking about the dot product. When it comes to working with vectors algebraically, we can perform scalar multiplication that we saw in the previous section, but multiplying vectors by each other is not as straightforward as we might like. There are a couple different ways that we have to approach this, and they produce very different results from each other. The first one that we're going to talk about in this section is the dot product. So if we take two vectors, vector A and vector B, the dot product of A and B is the number given by A dot B. So if we want to overemphasize that dot there, this is not A times B, this is A dot B is the way that we say that. That's going to be A1 times B1 plus A2 times B2 plus A3 times B3. So the way that we compute a dot product is by multiplying the corresponding components of the vectors and then adding those results together. So you multiply the corresponding components and add the results together. And in terms of just kind of the basic definition, that's really all there is to it. So let's try it out on a couple examples here. So -174 dotted with 62 -1/2. So that's going to be -1 times 6 plus 7 times 2 plus 4 times -1/2. So that's -6 plus 14 minus 2, which is 6. So a very important thing to take note of, the dot product does produce a number or a scalar. Okay, so in this case, the dot product between these two vectors is 6. For these vectors down here, so I plus 2j minus 3k, dotted with 2j minus k. So we're going to multiply the corresponding components. So we're going to have 1i, and then over here there are no i's, so that's a 0 component. So 1 times 0 plus the j's, 2 times 2, plus -3 times -1 for the k's. Notice the I, j's, and k's are not here anymore. So it's not I, j, and k because it's no longer a vector. Once you take the dot product, you are no longer working with a vector, you are working with a scalar. This is all numbers only from here on out, and that is 0 plus 4 plus 3, so that's 7. So the dot product of these two vectors would be 7. There are plenty of properties that we can look at involving the dot product. So here's some of our main ones. Any vector dotted with itself is equal to the length of the vector squared. So any vector dotted with itself produces its length squared. A dot B is equal to B dot A. So the order in which you do a dot product does not matter, right? And if you look at why that is, right, if you're multiplying A1, B1, if you switch them and make it B1, A1, it should be the same thing, and same for all of those. A dot B plus C is equal to A dot B plus A dot C, so it's distributive as well. C times A, so a scalar C times A dotted with B is the same thing as A dotted with C times B, which is the same thing as C times A dot B. So scalar multiplication can take place at any level of the dot product. Again, can be detailed up in here. So right, if the C is here or out in front of the whole thing, either way, it's the same. And any vector dotted with the 0 vector produces the number 0. Again, no longer a vector, just the number 0 if you dot it with a 0 vector. we can prove a couple of these properties. We can prove all of them. We are going to prove a couple of them. So we're going to prove the first one here first. And we're going to do all these proofs in V3. So for three-dimensional vectors. So we have A dot A. So that's going to be A1, A2, A3, dotted with B1, B2, B3. Or excuse me, it's A again. So it's another A1, A2, and A3. That's better. All right, so we get A1 times A1 plus A2 times A2 plus A3 times A3. So we have A1 squared plus A2 squared plus A3 squared. And if you remember the formula that we had for the length of a vector, the magnitude, that was the square root of A1 squared plus A2 squared plus A3 squared. All right, and this is that same formula without the square root. So what we could do, we could say that this is the square root of A1 squared plus A2 squared plus A3 squared squared. Right? If you take a square root and a square, they would undo each other, right? If we wanted them to, they could cancel and bring us back to here. But we don't want to cancel them because everything inside here, that's the formula for the magnitude or the length of the vector A. So that is the length of A squared. And we'll draw our little celebration box here. That lets us know that the proof is complete. But that's what we wanted. A dot A is equal to the length of A squared. And we're also going to prove property 3, so that distributive property for the dot product. So if we start off, so A dot B plus C. Might want to not write too big for this one. It takes up a bit of space. So that's going to be A1, A2, A3, dotted with B1 plus C1, B2 plus C2, and B3 plus C3. So if we dot those together, right, we multiply the corresponding components and then add. So we're going to get A1 times B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. And now that we're working with scalars, everything in here is a number now, right? No more vectors. The vectors are all gone. This is all just numbers. And we know that we can use the distributive property for numbers, right? That's something we learn in algebra. So now we can distribute all of these A's. So that's going to be A1, B1 plus A1, C1 plus A2, B2 plus A2, C2 plus A3, B3 plus A3, C3. And we can regroup these so that all of the B's are grouped together and all of the C's are grouped together. So we're going to have A1, B1 plus A2, B2 plus A3, B3 plus A1, C1 plus A2, C2 plus A3, C3 And these are the dot products of A with B and A with C. It's those formulas. So that is A dot B plus A dot C. And that's our property. So as with the previous section, a lot of these vector-based proofs, the work that is required, we need to combine, expand out, do whatever we need to do to get them into some scalar form, like with both of these. Once it's in the scalar form, we can then start playing around with it using the algebraic properties we know for numbers. And then in these cases, you apply that to a definition right here, or in this case, split it back up and turn it back into vectors again, right? So we turned it from vectors into scalars, and then from scalars back into vectors. And that's how a lot of these types of proofs go. Note, when you're talking about the dot product and you say it gives us a number, so like these problems back up here, so we got a dot product of 6, a dot product of 7. The natural question is, well, what do those numbers mean? We're going to get into it a little more in a bit, but basically the dot product describes a relationship between lengths of vectors and angles between them. So it's basically demonstrating the strength of the relationship between the vectors, whether the vectors are working together or working against each other. So it tells us if vectors are working together or against each other, and how strongly. So if the vectors are very long and they're both going in relatively the same direction, we're going to get a relatively large dot product because they're working together. If the vectors are shorter, then the value might not be as large. If the vectors are pointed kind of in opposite pointing directions, then there's going to be a fairly large negative dot product because the vectors are working against each other. And this relationship comes down to the following definition. So if theta is the angle between the vectors A and B, then A dot B is equal to the length of A times the length of B times cosine of theta. So this is another formula that we can use to define the dot product, and it very much is related by the lengths of the vectors and the angle between them, right? Those are the main pieces, the length of the vectors and the angle between them. So, for example, if A and B have lengths 4 and 6 respectively, and the angle between them is pi over 3, compute A dot B. So A dot B, so that's length of A times length of B times cosine of theta. So we get 4 times 6, cosine of pi over 3. Good time to brush up on the trig. That's going to be 1/2. And we're going to get 12. Right, so that's two vectors. The angle pi over 3 would be something like that. So So that angle pi over 3, one of them has a length of 4, the other a length of 6, so a little bit longer. But that gives us a dot product of 12. Now notice what happens when theta is pi over 2. So when theta is pi over 2, or in other words, 90 degrees. So when theta is pi over 2, we get A dot B is the length of A times the length of B times cosine of pi over 2. Cosine of pi over 2 is 0. So you take length of A times length of B times 0. So we just get out 0. So when the angle between two vectors is pi over 2, so when it forms that right angle between A and B, then that's going to produce a dot product of 0. So we say two vectors A and B are orthogonal. Now, orthogonal, this is a new word for us. Orthogonal essentially means the same thing as perpendicular, meaning that there is a 90-degree angle between the two vectors. We use this term a lot more in 3D because the concept of perpendicular really depends on working in a plane on that flat surface. So we use the term orthogonal a lot more frequently. So if you see this word, it just means that they're perpendicular. So two vectors are orthogonal or perpendicular if and only if their dot product is 0. So, and this is a very important property for us. So we can use this to determine whether vectors are orthogonal to each other or not. We can also construct orthogonality using this. We can do proofs with this. It'll be a pretty useful property to us. I want to look at an example. It's not typed up here, but I just want to look at a quick example. So R 2i plus 2j minus k and 5i minus 4j plus 2k orthogonal vectors. So if we want to determine whether two vectors are orthogonal to each other or not, we simply dot them together. And it's a nice, pretty quick test, because then if the dot product gives us a 0, then the answer is yes, they are orthogonal. If the dot product gives us anything else, then the answer is no, they are not orthogonal. So we get, in this case, 2 times 5 plus 2 times negative 4 plus negative 1 times 2. So that's 10 minus 8 minus 2. So that is 0. So the question, are they orthogonal? Yes, absolutely. They are orthogonal to each other. Now, when it comes to understanding this relationship between vectors and what the dot product is really telling us numerically, so obviously we saw here that it is related to the lengths of the vectors and the angle between them. The way that I like to describe this situation, the best kind of metaphor that I like to use is one involving Mario Kart. So if you're familiar with Mario Kart, they have these rainbow kind of speed booster pads that exist within the game. So hopefully everybody's at least vaguely familiar with what this is. So I've got my rainbow booster pad here. I've got the car right here. These booster pads represent like speed boosts, right? So basically what this pad is doing is if you drive on it, it is like a giant vector that's increasing your speed and pushing you this way, right? Now you yourself in the car also are going to have your own speed, right? You're going to have speed going in a particular direction, and as you turn the car, your vector turns with you. If you were to hit this speed boost, your vector and the other vector would have an effect, right? You would take your speed and the speed boost from this, and it would increase your speed, right? So you would end up getting some new vector. If you were to come at it from an angle, so say, you've got like your speed pad here, and you come at it from this angle right there. So we've got these two vectors. You're not going to get as big of a speed boost as if you hit it going straight on, right? If you just cut across it like this, you're going to get still a speed boost, right? Because you are going relatively the same direction here. You've got like a fairly small angle between them, but it's not going to be as big of a speed boost as if you were going like directly in that same direction. On the flip side, if you were to come at this from the other way, so say you're just messing around, and I know the new games, the mechanics don't work like this anymore, but this is how it used to be. If you came around it from this side and now you approach it from this angle, so say you're coming at it from up here. Now we have your speed going this way and the speed boost going this way. They are now working against each other. And so the dot product between them is actually going to be negative because now you're working against the speed boost. And the result in the game is that you slow down because the speed boost is trying to push you one way and you're trying to push the other way. Okay. Now, if you were to pass it like this, just go perfectly across like that. What the dot product tells us is by crossing at a perfect right angle, you are not working with the speed pad, nor are you working against the speed pad. So you're not going to get a boost in speed. You're not going to speed up, but you're also not going to slow down either if you're going the opposite way. You should just pass perfectly at the same speed. You should get no boost, nothing pushing you forward, nothing pushing you backward. You will have no change whatsoever. That idea of no change is the same thing as that dot product being equal to 0 at a right angle. Okay, so that dot product being 0, that's essentially what that is telling us. Okay, and you can use this to get further information about the idea of the dot product. If you have two vectors that are both pointed the same way, that's how you maximize that speed boost. That's how you maximize the dot product. You would get the maximum dot product if they're pointed exactly the same way. And if you have ones that are pointed exactly the opposite direction, that's how you minimize the dot product, right? You get it very, very negative if they're pointed exactly opposite. Okay, or anywhere in between as well. And of course, the longer the vectors are, the bigger the dot product's going to be. Okay, but it all balances out to 0 if you come at it from that perfect orthogonal angle, that perfect right angle. Okay, so, but this is a good way, I think, to try to visualize and understand what the dot product is doing for us. But that brings us to the end of section 10.3. In the upcoming section, we will look at the other form of vector multiplication that's a bit different from what we saw with the dot product, but that brings us to the end of this section.